So this is my project on finite size scaling in the 2D Ising model. So in our group project, we looked at the Metropolis Hastings algorithm. One of the tasks we focused on was the Ising model, and in particular coding it on MATLAB in both 1D and 2D. And in this project, I'm sort of building on that. So while the group project showed how the algorithm worked, I asked, how can you use finite simulations to learn about infinite systems while still using the Ising model? So the problem is that our simulation uses a finite box. So in the group project, we use 30 by 30 spins, but real magnetic materials have no boundaries, so they're effectively infinite. So we can't really take the magnetization from a small box and call it infinite. We need to find a way to obtain infinite from finite. So here's how I approached this. I knew I wanted some way to code this, but obviously you can't simulate infinity. So as I was researching this, I stumbled upon Lars Onsager's solution to the infinite Ising model in 2D in 1944. And I thought, what if I can use a method that lets finite simulations approximate infinite, and then obviously check it against the exact result? And that sort of led me to the finite size scaling theory. So what the finite size scaling theory tells us is that away from the critical temperature, which we touched on briefly in the group project, the magnetization of a finite system differs from the infinite limit by a correction of 1 over L. So that means if we measure the magnetization M for several system sizes and plot it against 1 over L, the result should be linear, with the intercept at 1 over L equals 0, meaning that L is infinite, giving us the infinite system magnetization. So to test this, I took our group project code on the 2D Ising model to run 5 different system sizes from L is 10 to 160, as I've shown on the slide. I chose a temperature of 2, as it's below the critical value and scaling is clean. I scaled the Monte Carlo steps with L squared so it would keep the stats consistent. The spin snapshots I've added on the slide show how the magnetization domain grows as system size increases. And these were my results. So as you can see, when I've plotted the magnetization M against 1 over L on the top, they do fall into a straight line. And then extending it backwards to give 1 over L is 0, which would represent infinity, gave the intercept M infinity is 0.909, which is my value of infinite magnetization. So I then compared the values to Onsager's exact formula, which his formula gave 0.9113 at t is 2. And my extrapolated value gave 0.909, so I was within 0.3%, which first of all, I was shocked was so close, but second, it showed that the simulation and the extrapolation method work. So why this worked? The linear scaling comes from 3 physical effects, which are proportional to 1 over L. Firstly, the boundary effects. So that just means that even with the periodic boundary, the boundaries, a fraction of the spins feel the finite volume still, and that fraction scales like 1 over L. Second, statistical fluctuations, which is that the uncertainty in average magnetization decreases like 1 over root L, which is 1 over L in 2D. And third, domain truncation, which just means that the magnetic domain can't grow larger than the box size L. And this explains why we got the straight line in our plot. Right, the rule is that the system size should be more than 10 times the correlation length. So in my case, the correlation size is about 5, so we need L is greater than 50. My data confirms this because at L is 80, we're within 0.3% of the infinite limit. At L is 160, within 0.1%. So, in summary, finite simulations can recover infinite physics. The method validated against the exact theory, and it provides clear simulation guidelines, so your system should be more than 10 times the correlation length. And that concludes my presentation. Thank you.